Okay, so today we are going to talk about another way that we use definite integration to find the volume of something, and that is called the disk method. So today we're going to use the power of definite integration to find volume instead of just area. Okay, so consider the graph of y equals x squared. So we know that that's going to be a good old parabola. Y equals x squared. What does the following statement represent? And we have the definite integral from 0 to 2 of x squared dx. So take a second and think about that. And if you're thinking in your head, oh, the definite integral from 0 to 2 of x squared dx represents the area under the curve and between the x-axis, between x equals 0 and x equals 2, aka this little slice of area right here, then you would be absolutely correct, okay? So today we are going to find the definite integral, not to find the area under the curve like we have in the past, but to find the volume if we were to rotate this curve around the x-axis. It is very important that we are thinking about what we are doing when we solve these problems. And this means that an accurate picture can make the world of a difference. So that said, let's draw what it would look like if we rotated y equals x squared around the x-axis between our same bounds, 0 and 2. Okay, so let's think about this. We have y equals x squared between 0 and 2. So I'm only going to draw it kind of over here. Y equals x squared. Actually, that's totally not enough space. I'm going to keep. There we go. That's enough space. And I don't like that drawing, so I'm going to restart. Okay, so we have y equals x squared between 0 right here, and let's say 2 is all the way out here, just so we can really draw a nice large picture. And so I'm going to actually redraw my parabola so it goes all the way out to 2, and then draw like a dashed line here. Okay, and we're again thinking about what would happen if we rotate this curve around the x-axis. So I'm going to draw a little rotating thing around my x-axis to remind myself, okay, I'm rotating this function around the x-axis. And so how I'm going to draw that is I'm going to kind of mirror it down here. And then I'm going to sketch out the 3D shape that it would form. So it would be kind of like a circle right here. Okay, and then there'd be like a circle right here. So hopefully you can kind of visualize the 3D shape that this creates. These are, for me at least, a lot easier to see than the cross-section volumes. Okay, and now our question is, how do we find the volume of this solid? And the answer to that is in much the same way that we've been solving all of our other integration application problems, okay? We're going to start with a small piece of volume and then sum up all of the little slices of volume to get, you know, an infinite number of infinitely thin pieces. Hence our depth is dx, okay? So what would a small piece of this shape look like? Hopefully you can see that if we kind of looked at this and made it 3D, and we can even draw this on like a separate axis, hopefully you can see that a thin slice of this figure would be a disk, right? So I'm going to add some volume here. And so this would be a slice of that figure that we're looking at. So that could be like right there. And hopefully you can see that that's a nice little disk. We could also draw it kind of sideways here like this, add a little bit of depth. I'm really trying to get better at drawing this stuff, guys. I promise. It's not as easy as it looks. Actually, I don't make it look easy because I'm terrible at it. But anyway, so let's think about how we might find the volume of this disk, right? So to find the volume, we need area and depth. Perhaps you can already guess that our depth is going to be dx, right? That arbitrarily small dx. And so that means we need the area. And so if we need the area of the face of a disk is in fact a circle, which is going to be pi r squared. So what do we need? Well, we need the radius, okay? And we can see in our image, the radius is actually right here. It's that green slice, and that green slice is going to be, in fact, top minus bottom, where top is our function and bottom is just the x-axis. So really, top minus bottom comes down to our function minus 0, which is just our function. Okay, so we know from this image, r is equal to x squared. So if we plug that back into our area formula, we get pi times x squared dx, which is equal to pi times x to the 4th dx, which would be the volume of one little slice. And then to get the volume of all of the little slices, we're going to take the integral from 0 to 2 of pi x to the 4th dx. And that's really easy to evaluate. You can pull out that pi. So we have pi times x to the 5th over 5 evaluated from 0 to 2. So it ends up that you get 32 pi over 5 for your final answer. Okay, so that was basically what all of this said. So if you want to follow along in the guided notes, you can do that there. And now we're going to generalize the disk method around the x-axis, okay? So if you open a calculus textbook or Google disk method, there's a formula that you will see. And what we're going to do now is generalize the process so we can understand where the formula comes from, okay? So we're going to draw a basic x-y axis, and we're going to use the actual same y equals f of x. So it's obviously our parabola from the last problem, but now we're generalizing it into some function, y equals f of x. And we're going to go from points A to B, again, so we could generalize. And we're going to draw that same shape rotated around the x-axis, right? So I'm going to draw this down here and kind of sketch a big old circle here so we can really see the 3D nature of our little shape. That one's not my best work, but hopefully you guys can see the 3D shape here. Okay, and so there is our generalized figure, and then I'm going to draw another small little disc in here so we could really focus in on a part of it. So here's my little disc right here, and I'm going to add some depth to that disc, make it really 3D. And again, we're going to call that depth dx. Okay, so just as we have been doing, we're going to use the volume of a small piece to find the volume of the entire shape. And so we know volume equals area times depth. We know that depth is dx. Area is going to be pi r squared because, again, it's going to be the area of a face, which is a circle. And so then the thing we need is radius. And we know that radius is once again going to be f of x minus 0. So if radius equals f of x, then volume is going to be equal to pi times f of x squared dx. And then that would be the volume of one small slice. And then to sum up all of the volumes, we're merely going to take the integral from a to b of pi times f of x quantity squared dx. Okay, so this is your little formula for the disk method. But again, be careful with this. It's important that you understand where it comes from so that you can kind of think about it this way every problem instead of just plugging and chugging, because plugging and chugging is no good. That will get you in trouble. Okay. All right. Part 3, disk method around the y-axis. So let us once again imagine that we have the graph of y equals x squared, except now, instead of finding the volume of a solid of revolution that is revolved around the x-axis, we want to find the volume of a solid of revolution that is revolved around the y-axis from y equals 1 to y equals 4. So again, let's draw what this shape is going to look like. So we have our axes. We have y equals x squared. And now we're going from y is equal to 1 to 4. Okay. And we want to rotate this around the y-axis. So I'm going to draw my little swirly thing down there because we're going around the y-axis. Okay. And so now I know that my solid of revolution is going to be this parabola, but starting at 1, mirrored around my y-axis. So it's going to come up like this. Let me move this over for myself, make a little bit more space, sort of. And then So we're gonna, for this, we're gonna have a sort of bowl figure, right? So if we go all the way up to 4, we're gonna come up to here, and we're gonna kind of have like this like, yeah, like a bowl, right? So we're gonna draw another little disc in here. Gonna have it right here. We're gonna add a little bit of depth. And that depth now, instead of being dx, is going to be dy. So I'm going to take this over here and draw my little disc like so. And this is going to be labeled as dy. Okay. And so now we want to, so we know y equals x squared, but now since we have dy, we want the problem in terms of y. So we're going to say x is equal to the square root of y, and that again describes our function. So now we know volume equals area times depth. Depth is dy, and area is going to be right minus left, which is going to be right, which is our function, minus left, which is just going to be the axis. And so our radius is just going to be the square root of y minus 0. So area is pi r squared because we still have a circle. R is equal to the square root of y minus 0, which is equal to just the square root of y. So if we plug that into our area, we get pi times the square root of y. I don't know why that square root turned out like that. Square root of y squared dy, which is just equal to pi y dy. And then to sum up our volume, we'll take the integral from 1 to 4 of pi y dy, which is equal to 15 pi over 2. Okay, so this is much the same as the disk method when we rotate around the x, but perhaps a little bit harder to see in terms of the image. And yeah, I guess that's it. It's pretty much exactly the same, except for you have to remember to convert your function to be in terms of y. All right, part 4, disk method rotation around a horizontal line. So conveniently, all of the above examples have involved solids that are rotated around the x or y axis. This is not always the case. Consider the graph of the function y equals the square root of x. A solid is created by rotating the graph of this function around the line y equals 1. The solid is bounded by the intersection of the two functions and x equals 4. What is the volume of the solid? So let's start with a good picture. I don't like those axes, so I'm going to try again. Okay, there we go. So y equals the square root of x is going to be in blue and look like that. Then we also have the line y equals 1, which I'm going to draw in green, like this. Y equals 1. And then a solid is created by rotating the graph of this function around the line y equals 1. The solid is bounded by the intersection, which I'm going to put in red right here, the intersection of the two functions, and x equals 4. And so x equals 4, let's say, is right here. Okay. What is the volume of the solid? So we need to draw this solid. So again, now we're going to picture that instead of mirroring y equals square root of x over the x-axis, we're going to mirror it around the line y is equal to 1, kind of like so. And then we're going to draw, again, our little disk figures right here. You know, right here, there's going to be one. I didn't do a very good job mirroring, but right here. And again, these are little 3D disks. And we're going to sum up the areas of all of them using a definite integral by finding the area of one of them. So volume equals area times depth. We're in terms of x, so depth is dx. Area is going to be pi r squared still. But now radius is a little bit trickier because it's not just our function minus the axis to get 0. Now it's going to be top minus bottom because we can see that our top function is going to be y equals x and our bottom function is going to be y equals 1. So our radius is in fact going to be top minus bottom, which is equal to the square root of x minus 1. So our area is going to be pi times the square root of x minus 1 quantity squared dx, and that is the volume for one little slice. And then to find the volume of all the slices, we're going to integrate from the intersection point, so we can set them equal to each other. Square root of x equals 1 if we square it. x equals 1 squared, so x equals 1. So we know it's going to be from 1 to 4. And then we can evaluate that integral relatively easily, and we should get 7 pi over 6. Okay. So not that much more complex, but definitely something to be cautious of, because again, no plugging and chugging. If you just looked at this problem and assumed it was normal disk method, you would get it wrong, right? So then part 5 is disk method around a vertical line. And I know this is kind of throwing you guys in deep water, but I want you to try and figure out this problem on your own, okay? So think about the way that we have done the previous problems, how we might write a function in terms of y, what the image looks like, what our radius is gonna be, that sort of thing. And we will go over it in class. So give us your best shot. I will ask for, a few answers here and there. I'm okay if you get it wrong. Like, I just want you to think through this and try it. So, the best way to learn is to, that's not true actually. But I do want you to try this because I think you have all the pieces to put it together potentially. So do your best. If you get it wrong, that's fine. We'll go over